started. So last week we talked about this very interesting state of matter called integer quantum Hall states. And so today we're going to talk about an even more interesting generalization of them, or extension of them perhaps, called fractional quantum Hall states. Before I begin, I just want to once again remind everyone that there is a luncheon the Saturday after my final lecture, December 10th. If you didn't get one last week, in the back, along with the handouts, there are RSVP forms. So you just, if at all possible, try to RSVP to bed by the 5th so we know that there's enough food for everyone. Right, okay, so what did we talk about last week? We talked about the following interesting physical scenario. Imagine, based on some clever experimental setup, I have a bunch of electrons in a metal, but they're really trapped in a two-dimensional plane, not like a bulk solid chunk of metal. It's really two-dimensional. And I apply a magnetic field transverse to that two-dimensional plane, and I cool the system down very cold. And what do I find that happens? For certain nice values of the magnetic field's strength, I find that this line here, which is the Hall resistivity, remember the Hall resistivity is I say apply an electric field in the x direction, and I find a net current flow in the y direction. Similarly, I apply a voltage here and measure a current flow here, and that how strong that current flows proportional to the electric field is something that's given by the resistivity. So this is the Hall or odd resistivity, and you find that it has these broad flat regions, and then it jumps down to another region and then another region. There's this other curve, which is the normal conductance, which just tells me as I try to apply an electric field in the x direction, how much current is actually flowing in that same direction. And what you find is that in these regions where current can flow perpendicular to your electric field, current cannot flow parallel to the applied electric field. That's the basic setup, and let me just remind you, the idea of this was the following. If I actually look carefully at what the density of states of electrons is in the system, and let me remind you, the density of states says that, so this axis is just the energy that we're looking at, and this tells me how many electronic states are there so that I can put electrons in. And the important thing was that these spotted regions are electrons that are localized and therefore do not contribute to either conductance, and these gray bars are extended states that can contribute to both Hall and normal conductance. So this is the picture, and so what you have is that if I have my magnetic field tuned so that I'm sitting here, I've occupied all of the electrons below here, and I see that the energy is in a region of localized states which can't conduct, so I don't get any conductance. As I change the magnetic field, where my band is moves down, and if I just happen to be sitting in the middle of an extended state, then I know that I can actually conduct normally, and that's why I have this peak in the normal conductance as the Hall resistance changes. And as I move through that peak, I now find myself again in a regime where the light excitations, the idea here is that this bar tells me how to excite an electron. If it's close to this line, it's easy to excite it. But so here in this region, the only electrons that are easy to excite are localized ones, and so it can't conduct. Whereas if I was in the middle of an extended band, then the states near this line are extended states, which just means that they can conduct. Hence, we find a region where we do get conductance. Right. Are there any questions about this?
So these are just electrical fields that you're showing?
This is just telling me where I can put electrons in the material as a function of how strong the magnetic field is. And the line is basically telling me how much room I have, because I have a material, there's a set number of electrons in that system. As I change the magnetic field, I change how many electrons really sit in these spots here. But okay, so there's something very nice about this, is that you find these resistivities have a very simple formula that in some particularly nice units, this is just 1/2, this is 1/3, 1/4, and so on and so forth. For various reasons, the usual normalization is that even though this is kind of a resistance of 1/2 or 1/3 or 1/4, we label it by 1, 2, 3. That's just a nomenclature thing. having to do with the fact that if I have more extended states available, I can have more conductance. More conductance, of course, means less resistance, right? If it's easier to conduct, it's not as good as a resistor. But something very interesting happens if you crank up the magnetic field strength anymore. So this is a different data, but basically the same thing. And so here, this is again that odd resistance, and this plateau here was that, you know, I equals 1 plateau, where you see here these these 4 different lines are just cooling the system down colder and colder. So you see when it's kind of hot, there's no plateau, but as I make it colder, there's definitely a flat region here. And this is the normal conductance. And you see the normal conductance is indeed going to effectively 0. And it turns out that as they crank the magnetic field up much, much higher, they saw this new plateau starting to appear at 1/3. And that doesn't make any sense from what we said, right? So here's our formula for the resistance, where previously this Greek letter nu was 1 or 2 or 3 or so forth. But in this state, this is a resistance where nu is 1/3, and that's why this is sitting at 3, whereas this is sitting at 1. And you may recall that this nu is related to how many states we've occupied. In particular, in these examples, right here, I've occupied 2, or I could occupy 3, and so on and so forth. So something very interesting is happening, right? And it turns out if you get cleaner samples and you make them colder and you do more precise experiments, you find a wealth of these very strange plateaus. And a plateau, of course, is just a region where this curve here, which is the Hall resistance, is constant for a reasonable range of magnetic fields. And the conductance, which is this curve down here, goes to 0. So here is that I equals 1 plateau, I equals 2 plateau, 3, 4. But we found a whole bunch of other ones, right? So here's that 1/3 state that we saw. But there's this whole wealth of all of these other plateaus. You might worry that, oh, these plateaus don't actually look very wide. That's actually just an issue of how this picture is scaled to try to show you everything. If you, of course, carefully zoom in on the data, you find that these are, you know, plateaus that are never going to be as wide as this, but they really are robust. And so let's look at this a little bit more carefully. Right? So something very interesting is happening. So again, this formula for the resistance goes as 1 over nu, which is what these numbers are. And so, of course, you find that as the resistance is getting bigger, these numbers are getting smaller. Right here I have 4, 3, 2, 1, and then just a sequence of fractions that are getting smaller and smaller. So something very bizarre is happening, because from our previous study of electrons in a magnetic field, this would never have happened, right? If I only have a partially filled level, I know that the system must conduct normally, but what we're finding here is this is a partially filled band that does not conduct at all. Right. So what's happening? If I neglect, I talked last week about localization and how localization is the physical thing that allows us to have these broad plateaus. And so we're just going to always assume that I can talk about things without that disordered localization, and we can always put it back in at the end, and things will work out. So ignoring that issue, with no interactions and no disorder, all electron configurations in one level have exactly the same energy, right? And what that means is that if I have no electrons, let's say, so I am down here, the idea is that this band would be unoccupied, nu would just be 0. If I have enough electrons to exactly fill this up all the way, that would be nu equals 1, and I would get a Hall conductance. In both of these cases, it's an insulator in the normal sense, that the normal conductance is 0. Okay, so we know what must be happening is something like the following. If I turn on interactions, and I just again ask the question, interactions mean that those electrons are going to bounce off of each other, but I can still talk about how many electrons I have in the system and what states I can put them in. It's just not simple kind of free streaming particle states anymore. And what has to happen is that that one line gets broadened into some wider distribution, and that distribution has to have gaps in it. It has to have gaps in it because we know experimentally that we have these plateaus appearing. And so this is kind of just crudely pictorially, right? The idea is that this is that gap that gives me the 1/3 state, 2/5, 3/5, 2/3, 1, etc. So we can kind of follow along here, right? If I have just enough electrons to fill up just this lower chunk here, I'll see this plateau. And then as I add more, you know, if I And then if I had just enough to fill up this next chunk, I get this 2/3 plateau, and then skipping over a whole bunch, because I can't draw a fractal in here, right? I mean, there are lots and lots and lots of subdivisions of this. If I have just enough to fill up to this opening, I get this 3/5 plateau, the 2/3, and then I'm back up here in this nice plateau where there's a big window. Right? Yeah, so as I decrease the magnetic field, the size of the electron orbitals as I decrease the magnetic field, the size of the electron orbitals gets bigger, and so the actual number of states in this band is getting bigger. But I don't want to have to rescale the plot every time I shift it. But the idea is that you of course have a sample. I'm not adding and subtracting electrons. I'm really just changing how many electrons actually fit in this chunk of the number of states. So the important thing that I want to emphasize here that I can't really draw nicely is that it's clear that there's not just some finite number. If I really can do this very cleanly, it looks like there's a nearly fractal structure, right? Here I have these funny sequences that seem to be approaching 1/2, and over here I have a funny sequence of plateaus that are approaching 1/4. If I 3/4, there's a 1/4, and so forth. Down here, even above filling 1, there are more of these fractional states. So something interesting is going on, but roughly the idea is this, that interactions are taking my one contiguous, very degenerate band and breaking it up into a whole bunch of different ones. So this is a very complicated story, and what I'm going to focus on today is just trying to understand the physics of kind of the most robust plateau we have that's fractional, which is this 1/3 state. So, and I'm going to talk about how the 1/3 state is very different from that trivial integer state, right? So this was, again, a plateau that we understood just by thinking about free electrons in a magnetic field, and this is a plateau that we cannot understand. If we just think about free electrons in a magnetic field, there's no reason for this to be flat, and there's no reason for the normal conductance to be getting small. Yeah, and I just want to emphasize, this number, nu that I talk about, especially when I'm talking about numbers between 0 and 1, it's just the number of electrons we actually have divided by the total number of electrons in that original Landau level. So this is that kind of broadened Landau level. If I have no interactions, this is just one big lump. And so if I fill up, say, some piece of it, I get maybe 1/3 of the number of states in here. If I fill up all of it, I get exactly nu equals 1. So nu is just counting how many of these states I end up occupying. And as we argued based predominantly just on the experimental results that we saw, we know what has to happen, again, is that these distributions of electronic states have to get split up so that if I have exactly 1/3 of the number of electrons that live in this total thing, that means I just fill up this bottom chunk and I don't have to worry about being in the middle of a band. So it won't conduct normally. All right. So one of the reasons that I'm going to focus on this 1/3 state and the 1 state, well, one reason is because it got a bunch of people Nobel Prizes. But another reason is it's a simpler thing to look at. So let's remember in the non-interacting problem, we have this organization of states. And so remember that in each one of these energy levels, the number of states in each energy level is proportional to the magnetic field strength times the area, right? So, which is basically if I took the magnetic field strength and integrated over the size of the sample. That number is basically up to numerical constants. That's the number of states that I have here. And these states in this lowest level are kind of very special. There's a mathematical property they have that makes them much nicer and much more constrained than these other states. The idea is they have a mathematical property called, they're holomorphic. So the idea is that normally a wave function for an electron in 2 dimensions is a function of both of its coordinates, right? I can say where is that electron as a function of where it is on the x-axis and where it is in the y-axis, right? So there's something very special that happens if I have any state, and so I don't just mean, pictorially this state here or this state here. I could also take a linear combination of this state and this state, or a superposition of 3 states, or whatever I want. All of those states have wave functions that have this very special property that they're not just a function of x, they're not a function of two variables, they're really secretly a function of one variable, which is a complex number x plus iy. Now, if I had something that was a function of x plus iy and x minus iy, I could then just rewrite that as a function of x and y. But here the rule is that no, it has to be a function of this very special combination. You could think of this in a couple ways. You can think of this as basically saying this function is so constrained, it's not really a function of two variables. It's really a function of one variable. And so what that really means is that there's less room, there are less ways in which the electron's wave function can be spread out in space. Another way of thinking of this is basically all of these states in the lowest Landau level are electrons orbiting with the same cyclotron frequency. That's a semi-classical picture, but that's roughly what this means. So we can kind of see some pictures. So this is a nice holomorphic wave function that just has spin 1. So you see it's rotating at some frequency. This is, some pictorial representation of the wave function. Here's a state with spin 2. You'll notice that that was the same amount of time. It looked like, and it came back to itself in exactly the same way, right? So this is also rotating at the same frequency. And similarly, this is much more complicated. So this is essentially a superposition of an electron here and an electron here. And we see as this time evolves, it does something funny, but it still kind of comes back to itself in that same fixed amount of time of one cyclotron orbit. So the idea is that this is a quantum mechanical version of saying all of these electrons have to be going in orbits that take the exact same amount of time to go around it. Okay, so we've talked previously about single particle wave functions, and we know that if I need to talk about more than one electron, I have to talk about multi-particle wave functions. And so the idea is that if I have a multi-particle state, something that's describing more than one electron, as I clearly need to do here, then those wave functions also have to have this very special mathematical property that they're holomorphic. But that can be a little bit of trouble because interactions are going to make these guys talk to each other. And so, if I have Coulomb interactions, I might worry about this electron talking to a virtual electron that could live here, right? So this doesn't work if I have mixed states. So let's say I have interactions, and the interactions tell me, for whatever reason, that the state that I need to look at is, say, a linear superposition of electrons in the lowest level plus some electrons in more excited levels, right? Well, as soon as I have to worry about electrons in more excited states, then this beautiful mathematical property is just dead in the water, because these states up here don't satisfy it, so it doesn't work. So if we want to use the powerful mathematical machinery of this holomorphic constraint, we need to somehow include interactions, but be able to ignore these higher levels here. So we have to take some sort of separation of scales. Okay, so imagine I have some, let's say, partially filled level with no interactions. It's partially filled because we know that the 1/3 state has enough electrons to only partially fill this lowest energy band. So if I have this with no electrons, well then it's just going to be some boring thing where I have some superpositions of electrons occupied in this lowest band and no electrons in this higher band. But as soon as I turn on interactions, as we said, this is out the window. What you'll find is that, okay, this faintness here means that there's some superposition of states in these lower band, and also there's some superposition in states in these higher bands. But the important thing to remember is that there are two energy scales in this problem, right? The first energy scale is just the original non-interacting gap between how much it costs to put electrons in this level versus how much it costs to put electrons in this level. In other words, how much it costs to take an electron from down here and pop it up here. And that's the cyclotron energy. It scales with the magnetic field. It scales as 1 over the electron's mass, so on and so forth. There's another energy scale which just says I turn on Coulomb interactions. And if I turn on Coulomb interactions, I can ask, what's the energy scale of those? And it's roughly, well, E squared, because E is the charge of these electrons, and it's 2 electrons interacting. And then I need to put in the length scale, so let's just put in the magnetic length. And these two things go very differently. First of all, this scale depends on the mass. This doesn't. This just depends on the electric charge or the magnetic field strength. And so the question is, can I take some sort of limit to pull these things apart? And it turns out you can, right? I can kind of imagine formally considering a system where this little e is so small that this goes as e squared, this goes as e. So if e is very small, then what basically happens is that this energy scale goes to infinity relative to this energy scale. And I can just ignore these states up here. This is something that's called the lowest Landau level projection. What it just means is that for the time being, I'm going to ignore the fact that these other states exist, because at the energy scales that I'm going to study this system, I'm never going to probe the system in such a way that I really have to worry about kicking electrons all the way up here. If I kick the system, I'm going to take an electron here and move it to some other state at a nearby energy. All right? In this limit, I retain this beautiful holomorphic constraint that now I have a wave function that originally depended on the x and y coordinates of each electron I was keeping track of. And now it just depends on this special combination. So this is a function of one variable for each electron instead of two. So it's much, much more constrained. So I apologize. I'm going to have to write down some formulas. So based on just these ideas alone, we can actually write down from that constraint of the holomorphicness and making sure that we have the right number of electrons in the state, that completely fixes what the many particle wave function for that easy nu equals 1 state was. Right? I probably could have told you this last week. There are a couple constraints. I need to make sure that if I ask what's the total charge density of this wave function, I need to make sure that I get 1 times the magnetic field strength times the area, because this 1 here is the thing that tells me that nu equals 1. And holomorphy, and there's an additional constraint that is just that these guys are electrons. And so if these guys are electrons, remember that we said previously, for electrons, they're fermions. So if I take 2 electrons and exchange them, I have to get a minus sign. Right? And that's clear from this construction here, right? Because here I have 1 minus 2 and then 1 minus a bunch of other guys. And so it turns out that if I send 1 to 2 and 2 to 1, this changes sign. These two terms change sign, but they cancel. And everywhere else, things that you worried about cancel their sign changes. And so this is the unique wave function that I can write down that satisfies the 3 properties. It satisfies this kind of mathematical holomorphic constraint that it's secretly a function of 1 variable for electrons, not 2, such that all of these electrons really behave like electrons in the sense that when I exchange 2 of them, I get a minus sign, and that I have and then I have the right number of electrons. Right.
Is that a form of series that's being shown?
So what I'm doing here is I'm working with a finite number of electrons, right? So I'm saying my sample has finite size, so there really are a finite number of electrons in there. Now the number order of the number of electrons is a big number. Even for these samples, they're kind of small, but it's still order 10 to the 10, 10 to the 11 electrons. But we're doing the best that we can here. But this is really a finite product of these things. When they try to put these things on a computer, it's very, very hard to actually try to solve this numerically as soon as you have more than like 10 electrons. But so, as I said, what are the contents of this wave function, right? So I said that it has to be odd as I exchange 2 things. That means that it's clear from this that if I take it, so these are just the coordinates of where the electron is. And so if I try to take 2 electrons and put them near each other, the wave function vanishes. And it had to do that, right? Because there's a Pauli exclusion principle that says I can't have 2 electrons in the same place, in the same state. So this automatically does that. What actually happens is that the probability of finding 2 electrons near each other goes as their separation squared, right? So they really can't get very close to each other. And this is the weakest constraint that you can have for electrons. There's this exponential factor that's important to make sure that I really have a finite volume. But you can kind of go through the machinery of just doing the quantum mechanical calculation. You find that this wave function gives me the correct charge density, it gives me the right Hall conductance, it is an insulator, and so on and so forth. Moreover, it's not at all obvious from this formulation, but it's true, that this state is incompressible. What do I mean by that? If I just have a gas of particles and I try to put a density wave in it, as long as that I can do this at arbitrarily low energy costs, as long as I make the wavelength of the density wave very, very long. Right? You can just think about that of moving air. Right? You can always move your hand through air, and it doesn't cost some finite energy barrier if you move slowly enough. On the other hand, for this system, these electrons are really incompressible. The idea is that if I try to squeeze them or stretch them a little bit, there's a finite energy cost, right? Much like think of water, right? You can't take water and compress it; it's incompressible. It's the same thing here. So there are no sound waves in this system, and as I said, there's a minus sign as you exchange them. The idea being that here is one of my electrons, here is the other, and as I go forward in time, if I move one to one side and one to the other, the state has to come back to minus itself. That's just a property of these being electrons. All right? So this is this very lovely explanation of a state that we already understood, right? We already basically understood, based on just single free electrons, why we had those integer valued plateaus. But I need to tell you about this formalism to be able to talk about the fractional states, because it was in that realm that Bob Laughlin was able to make is absolutely brilliant, and calling it a guess is really a misnomer. It was a very well-guided, intuitive choice. It was not really a guess out of the ether. So this is this very famous paper where he wrote this down in 1983. And his guess was the following, right? He basically took that previous formula and he changed one thing. He changed one thing. He said, this previously was just the power 1. I'm going to change that to a 3. So let's ask a couple questions. First of all, is this still a good description of electrons, right? Well, if I exchange these two, I get minus 1 cubed, which is still minus 1. So this is still describing electrons, right? But remember the probability, which is just the wave function squared, so that means that the electrons are further apart. The probability goes as their separation to the 6th power. So it's much, much harder for electrons to get closer to each other. Why is this happening? Well, so this was just a guess, but physically what's happening is that I have a bunch of electrons in a material, they're charged, and they all have the same charge, minus 1. And so as they try to get near each other, there's an electrostatic repulsion. So it's perfectly natural to assume that these electrons don't actually want to get near each other, and they're pushed further apart by these interactions. You can kind of see that. So here is kind of a crude picture. If I just say, based on using the wave function as a probability distribution to get a reasonable guess for where electrons can be, here is a picture of where electrons can be for the nu equals 1 state. Here's a picture for where they can be for the nu equals 3 state. You can see they're much further apart. They're spaced out. On long length scales, they all have basically the same spacing, though there's, of course, some random distribution on shorter scales. And what actually happens is because of this 3 instead of 1, you can go through the mathematical machinery to quickly discover that because the electrons are on average 3 times as far apart, the charge density of this state is 1/3 of what it would have been for the nu equals 1/3. Well, charge is just counting how many electrons are in there. So this uses 1/3 as many electrons as the nu equals 1 state, and that means that by definition it is the nu equals 1/3 state. And you can basically use the same arguments that we used previously to say if I have a state and it has some filling fraction, whether it's an integer or a fraction, as long as that state is gapped, by which I mean the number of electrons completely occupy some little chunk, and then there's a window to find in energy spacing to find new places to put electrons, then the Hall resistivity has to have this form. This would have been a 1/nu, 1/nu is 3, so you get this answer, and this is, of course, exactly what they saw experimentally. But this was just something that we wrote down, right? What does it actually have to do with electrons interacting? I had this story where I said, as electrons get near each other, there's a repulsion, so they shouldn't be allowed to get as close to each other. But that's a story. But you can actually show that if I say that my electron-electron interactions aren't exactly what Coulomb interactions look like, but it's something a little more fine-tuned, then this is an exact solution to the quantum mechanical problem. And moreover, you can prove that there is a finite energy gap to the next excited state. If you actually really ask the problem of, what if I have honest-to-God Coulomb interactions in this material, then what you'll find is that it's very, very close. You know, say for 12 electrons, this guess has about 99% overlap with the actual exact answer that a computer will tell you. So you know, there's a lot of really good physical intuition in this guess here. And I mean, it was this intuition that led him to this. It was not really just something he invented. Are there any questions about this? Yeah.
What happens if you change that exponent from a 3 to a 5 or a 7? Would that cause any changes?
That's a fantastic question. What you would indeed find is that what's going to happen is that, let's say I make it a fit, and this is actually in Laughlin's paper. If this is, right, so as you clearly noticed, it can't be an even number, because if it's an even number, they're not electrons, right? Because electrons are fermions. So let's say it's an odd number, and let's make it a fifth, or make it 5. Then the electrons are going to be on average 5 times as far apart. So the filling factor will be 1/5, and this will be 5h over e squared. And there's actually an interesting story. It wasn't in that plot I showed you of the experimental data by Sui, Stormer, and someone else whose name I tragically forget. In that plot I showed you, just go back, this exciting state that they saw was really here at 1/3, and you'll notice that this plot doesn't quite go far enough to show 1/5. And the story, which may be apocryphal, I don't know, goes as follows. Bob Laughlin had this idea, and he realized that that 3 could be a 5 or a 7 or something else, but he was nervous about publishing his result until an experimentalist told him, this wasn't something that was published, an experimentalist told him that they had seen hints of a plateau when they cranked the magnetic field up to 1/5.
Question.
Yeah?
The little diagram up in the upper left, is that like the sample?
Oh, yes. So this is a picture from the Sui et al. Paper. And so this is really kind of an idea. This is your piece of metal here, and these are metallic leads that are attached to it. And it's a pictorial diagram of you drive a current through here, and then normal resistance is measured this way, and odd resistance is measured this way. So this is, yeah, this is just a picture of the actual, I mean, it's a picture of the actual thing they were doing the experiments with. But you know, I had a hard time, I tried to find it, I had a hard time tracking down actual experimental results for that, you know, Z1 minus Z2 to the 5th state, which would be, you know, way up here at 1/3. I've been told it definitely exists. I just couldn't find the actual experimental plots. It is worth emphasizing that it can't actually get too big. There are physical arguments that say that if I change this 3, not to a 5, not to a 7, but if I make it really, well, I think even maybe it's at 7, it turns out that this, while it is a solution to the Hamiltonian, it's not actually the lowest energy solution. And the system really looks like something different. It turns into something called a Wigner crystal. A Wigner crystal is, right, so here, my electrons are like a fluid, or they're like a liquid. Why are they like a liquid, right? Because they can move around, but they're incompressible. Right? Whereas in a normal metal, electrons are like a gas, right? I can have waves of electrons go through a regular metal or a superfluid. I can't imagine that the electrons get so pinned down that I can't even move them, right? They're really pinned in some lattice structure, and that's what a Wigner crystal is. And it's believed, but I don't actually believe that there's robust experimental evidence for it. It's believed that if I crank up the magnetic field high enough, this system will actually turn into a Wigner crystal. But that's, you know, I think at the moment that's conjecture, and there isn't actually experimental evidence for this. The tricky part is that, of course, remember, the fundamental length scale of this problem is this thing called the magnetic length. And the magnetic length I don't think I have the formula in these slides here. The magnetic length goes as 25 nanometers divided by the square root of the magnetic field in Tesla. And it turns out that if I really try to just extrapolate these diagrams and crank up the magnetic field that high, then the magnetic length, the size of these orbitals that the electrons are going in, starts getting too small, and it gets down to the scale where I have to worry about the actual lattice structure of the material. So for these materials, it's not really actually clear that you'll ever find a Wigner crystal, because at some point the electrons are trapped in such tiny orbits that they don't look like a free gas, right? The original story that I talked about last week was that as long as the magnetic field isn't too strong, the size of the orbits the electrons are going in are significantly bigger than the details of the size of the underlying ionic lattice of the material. And if they're in big orbits, they can kind of, it's kind of blurred out the details of that fine structure. But if I crank up the field too high, they will start to see it again. So that's a reason, it's also just hard to get samples of these extremely high magnetic fields. So it's hard to produce them. Yeah.
And again, is this model true for all types of metals? Like lead, gold, iron?
No, you have, I mean, no, you have to have a system such that whatever the details of how you construct it, you have some semiconductor layer put on some substrate, however you build it. The important thing is that it's a reasonable approximation to say that before I apply magnetic field, what the system just looks like is a essentially infinitely thin sheet of metal, so that the electrons move in 2 dimensions. And a normal material just won't have that. You can't get it thin enough. It's very hard. That's actually one of the reasons that I'm not going to be able to talk about it today, but there's a version of this integer and fractional quantum Hall states in graphene. You guys may be familiar with graphene. It's basically, you take a piece of Scotch tape, you put it on a piece of carbonite, you pull it up, and you get an almost perfect, basically 1 atom thick layer of carbon atoms. And even though that doesn't sound like it is, that one kind of 1 atomic layer thick layer of carbon atoms in this hexagonal lattice also looks like a 2-dimensional electron gas, in the sense that there is 1 free electron that per, well, 2 free electrons per site that can hop around, and they really just look like a metal in that sense. So the answer is that you have to kind of cook up very clean and nicely constructed materials such that they look like 2-dimensional metals. And they need to look like very clean 2-dimensional metals. If they're too dirty, if I have too much disorder, none of this story works. So that's one of the difficulties in experimentally doing this, is you have to try to make these samples, and you need to make them kind of really, really clean, so that treating it as electron in a kind of very weak background disorder is valid. If it's really dirty, then then disorder isn't a small perturbation, and it dominates things. So
let me ask, do you need a special type of machine to get that slice of metal?
So usually what's actually, I'm certainly not an experimentalist, but what they basically do is they'll try to grow a sample in the way that you kind of grow a crystal. It's not exactly the same thing, but you grow a crystal by having some gas of atoms, and you let them cool down, and they'll just naturally, as they cool down, they'll form some crystalline structure. So in that sense, people grow these samples, right? They have some substrate, and they put in a bunch of atoms, and they want those atoms to kind of cool down and form a thin layer on top of the sample. I mean, that's a field that I'm certainly by no means an expert in. It's a very, very difficult problem. But clearly, from our plot, people are able to do it for a lot of these things. Are there any other questions? Yes?
So this bigger crystal is really not, it's not something that exists in kind of normal states?
No, a Wigner crystal is something that is conjectured to exist if I really crank up the magnetic field extremely, extremely high. And again, at least in these examples, I think it is really just a conjecture. There are numerical studies, right? People take toy models and they put them on a computer, and they say, okay, computer, how high does the magnetic field have to be before the right state is a Wigner crystal? But that's different than actually seeing it in the laboratory. It's certainly, there's numerical evidence for it. but I don't think there's actually any solid experimental observation of it.
So all of these magnetic fields must be like generated by cryogenic magnets, right? I mean,
Yeah.
that are still laboratory size.
Yeah. Yeah, I mean, that's how you do it, right? You take your sample, you have some superconducting magnet because you need to be able to get it very, very strong. So you want a superconductor so you can drive currents very fast, because the harder you drive a current, the stronger the magnetic field is. Yeah. Okay. So this is Laughlin's great guess, that he has this very nice prediction for how the electrons behave. But that's actually not all there is to this story. It gets much weirder. It turns out that you could just change his answer a little bit by saying that there's a defect. There's a defect in this state. So what do I mean by that? So remember, these z's are all coordinates of the electrons. And when I say I put in a defect, I just say I'm going to multiply the wave function by some prefactor that says the wave function vanishes linearly now every time any electron gets near some point at coordinate zeta. Okay? And I want to emphasize, right? The z's are electron coordinates. This is some basically external parameter. It's this defect that I tried to add to my state. And it turned out it's a heavy object, and it has a lot of strange properties. It's by no means obvious from this construction, but you can kind of sort of believe it. There's a hand-wavy way of arguing this that isn't quite true, but it works for a lot of these states. These are electrons, and they have a power 3. This state has a power 1, so this guy has charge 1/3. That's a cheat, but for the examples that I'm going to talk about, it basically works. So I have this defect here, and the point is that since the electrons can't get close to it, but it's not like they can't get close to it as strong as they can't get close to each other, that means that there can't be as many electrons near this region as there are everywhere else. And what that means is that there's less charge here, but how much less charge is there? There's actually 1/3 of an electron's charge left. So this funny defect that I put in the system seems to violate kind of standard quantization. It's a defect that doesn't have the charge of 1 electron or the charge of 1 proton. It has 1/3 the charge of an electron, except the opposite sign, right? Electrons are negatively charged, this guy's positively charged. So this is something very puzzling, but it's just something that falls out of this formalism. Now, you can weaken things and say, well, what if I want to allow the defect to move? Well, I told you it's charged, and it has some weight. So if I let it move, it's going to also move in some cyclotron orbit, but it's going to move in the opposite direction as the electrons, right? The electrons, let's say, move in clockwise cyclotron orbits because they have a minus sign. This guy has a plus sign, so it's going to move in counterclockwise orbits. Okay. But they're going to have even stranger properties than that. Okay. So let's remind ourselves of something I talked briefly about in the first week. Why, when we normally talk about particles, fundamental particles, we say there are only 2 types of particles that we can have, bosons and fermions, right? Either even or odd statistics. Well, without getting into the details of the mathematics, the idea is the following, okay? So what are we talking about when we talk about statistics? Here's the yardstick here, it's much more helpful. Does anyone see like a large yardstick? I should have looked for one earlier. Well, okay, I'll try to make do. Okay, so I have 2 particles. And the question is, what happens when I exchange them, right? If I take 2 particles and I exchange them, well, from the point of view of one particle, what does that look like? That looks like one particle wrapping around the other 180 degrees. Now, that might not be obvious, so I'm going to try to kind of make it pictorial, right? So let's imagine this. I know this is hard to see, and I apologize. If anyone else has a cane or something I could borrow. So this is one particle, this is another particle. And I exchange them once, so they just move to other spaces. Now, what does that look like from the point of view of one of the particles itself, right? Well, it just looks like this guy went from over here to over here. So it's a 180-degree rotation, right? Is that clear?
Yes.
Good. Okay. So if I exchange them once, and then I exchange them again, that's a 360-degree rotation, all right? So braiding twice is the same as a 360-degree rotation. Now, mathematically, the reason that fundamental particles have to have plus or minus 1 is the following. Well, it's because there's no topological obstruction to the following. So here is a 3-dimensional picture, there's x, y, and z, of my one particle, and I wind it 360 degrees around the other particle. Okay? But I can smoothly deform this path. I can just lift it up and shrink it down to 0 size, right? So the idea is that if I just think about the topology of this path around this other point, this curve here is topologically equivalent to this particle not doing anything at all. Is that clear? Right, I have a rope sitting around something, but if I have 3 dimensions, I can just lift it up and pull it over the point. Right, that's clear? Yes, no?
Can you explain that again?
Right, so here's a picture of my one particle, and it loops around the other particle. Okay, but this is a loop in 3 dimensions, and so I can take this loop and lift it up a little bit, so it's now above that point,
Okay.
and then I can just shrink it down to 0 size, and it never gets stuck on this other point. Okay?
Do they ever touch?
No, that's the point, is that I can shrink this loop to 0 size without it ever touching the other particle. That's a great question. Okay, so since exchanging twice is the same as doing nothing topologically, that means that if 2 exchanges has to be a +1, then there's only one possibility for 1 exchange. It can only be +1 or -1. And that's the simple mathematical reason that for fundamental particles there are only bosons and fermions. Is that clear?
Yes.
Okay. But we're talking about some effectively 2-dimensional system, right? Where we're looking at defects that are really just living in this plane. So we have to ask, what does braiding and statistics look like there? We're braiding in a plane. So now I only have an x and y direction, and I wrap this guy around this other guy, and it's clear, if this is confined to a plane, right? So here's a different version of this picture. I have an x and y, and now I'm just plotting the lines as a function of time, right? So this is the world line of each particle, and it's clear that the world lines live in 3 dimensions, not 4 dimensions, right? For points in 3 space, if I include time, that's a 4-dimensional world line. And it's clear that if I take this one particle and I say, wind it around the other, I do that 360-degree rotation as a function of time, there's no way that I can deform this curve to pull it back to be a straight line, right? So, because I'm in 2 dimensions and not 3, I can no longer make the argument that exchanging twice has to give me +1, right? It's a special property of these things being confined to 2 dimensions. There is one constraint, which is that it's clear that in 2 dimensions, there are of course 2 different ways you can braid, right? I can go counterclockwise, or I can go clockwise, right? So here I'm going counterclockwise in the exchange, here I'm going clockwise in the exchange. So this picture is reasonably clear. It's just me trying to exchange these 2 particles. But it's clear that if I go counterclockwise, and then I follow it by going clockwise, I get this picture here, right? But in this picture, there's no constraint, right? I can clearly just pull this line back and pull this line back, and I get 2 straight lines. So what that means is that since a counterclockwise rotation followed by a clockwise rotation is the same as not doing anything, that means that a counterclockwise rotation that a clockwise rotation has to be the inverse of a counterclockwise rotation. Now, if I'm just talking about electrons in 2 dimensions, this is fine, because the inverse of -1 is -1. But that's not all I'm allowed to have. I can basically have an arbitrary phase. So here's a picture of, in my complex plane, here's the phase for a clockwise rotation, here's the phase for a counterclockwise rotation, and to people who remember enough complex numbers, it's clear that the product of these 2 things is just trivially 1. But that's the only constraint, is that when I talk about braiding, I always just have to specify, am I doing a clockwise or counterclockwise rotation? And now it's not obvious, and I haven't proven this to you by any means, but it's true that I can ask, okay, we knew just from looking at the wave function, basically, it's a bit of a cheat, that if I exchange 2 electrons, I get a -1, okay? There's actually a more careful mathematical way of calculating what really happens when I exchange 2 electrons, but I'm not going to go into that in too much detail right now. So I can just ask, what about our defect? So in this 1/3 quantum Hall state, we know that there exist these defects that have charge 1/3. And you can ask, what's the phase you get when you exchange them? You grind through the machinery of the calculation, and you get the following very strange phase. You get -1 to the 2/3, or I, yeah, or yeah. So it's a 3rd root of unity, So what does that mean? That means we have to exchange them 3 times to get back to the original state, right? I exchange them once, I get minus 1 to the 2/3. I exchange them twice, this obviously should be a 4/3. I exchange them again, I get minus 1 to the 6/3, and 6/3 is 2, and so the product of these 3 guys is in fact plus 1. So I have to exchange them 3 times, right? So these properties are very funny. But there's something even, and it still gets weirder. Okay, so I just told you about these funny defects that exist in this system. And you might ask, well, how do I actually get one of those in there, right? That seems like a hard problem. There's an easy way to put these defects in the system. Well, easy maybe at the level of thought experiments, right? I have my sample, and what am I going to do, right? Well, the defects have positive charge, so I need to be able to remove charge from the system. So what do? I take 1 electron in here, and I pull it out, okay? And you would normally think that, okay, that just means that there's just some electric charge deficit here, so there's what looks like a hole, or a particle there that has charge plus 1. This, of course, costs some finite energy to do. But what actually happens in the system is that when I pull this charge minus E out to get a charge plus E remaining, it doesn't want to just stay a charge plus E. It actually wants to fractionalize. It wants to split into 3 different defects that then go off on their merry way. So in this way, you really can't actually construct these guys. I mean, it's of course experimentally more nuanced than this, but these are real excitations of the system, right? Now, you of course worry that, well, if I'm talking about systems where I have excitations that have charge 1/3, that seems very troubling because it's a material made out of electrons and nuclei. Now, of course, if I just take a sample and I cut out a chunk of it and I ask, what's the total charge in that sample? You'll find that the total charge in that sample will, of course, always be an integer. And the reason for that is that I'm drawing these as localized defects, but that's a little bit of a cheat, right? Because this is a quantum mechanical system, and in a quantum mechanical system, right, these guys have some spread. And so if I try to, say, cut the system here and ask the total charge, I know that I must be doing something drastic to the wave function. And when you work out what that drastic thing does, if I try to do that carefully, I'll find that cutting the system between these different guys will disturb the wave function in such a way that on both sides I will, in fact, have an appropriate integer number of electrons. But as long as I'm just asking locally what are local charges, it is completely possible to have localized regions of fractionalized charge. And it's worth emphasizing that this isn't just a theoretical pipe dream. There are experiments that people have done where they have looked at kind of local charge mobility of these states and found that experimentally the results they see could only occur if there were charged objects that had 1/3 of an electron's charge. Yes?
Now, is that grouping what you talked about earlier, anion, or?
Yes. So these are anyons. So them having fractional charge isn't what makes them anyons. Anyons specifically refers to having particles such that when you braid them, such that when you exchange them, you don't just get plus or minus 1. Yes, the nomenclature for these guys is anyons. There are, of course, whole hosts of other types of states you can have.
To stay in a group, right? I mean, they would want
Once I put these guys in here, no, right? No. This guy can move over here, this can move over here. I mean, they can separate. That's the important thing. They obviously can't separate too much because the sample has a finite size, but they don't have to stay near each other. The important thing that I want to emphasize is that this isn't in contradiction to actual charge quantization, because these are kind of topological defects built into an extended wave function that is extended on the whole sample. If I really try to cut it and measure a localized charge, I destroy that extended wave function structure. Another way of saying that is that when I put these guys in there, they are very non-trivially entangled with each other, so that if I try to cut the system, I'm doing something extremely drastic. So it turns out, and again, I'm not going to go into too much of the details of the mathematical machinery, is that for at least this nu equals 1/3 state, all we need to describe this fractional Hall resistance is the fact that we have these anyons in the system, and we have to know what their charges are and what their statistics are. If you just know those ingredients, it turns out that you don't actually need to keep track of the whole wave function for all of the electrons. Why don't you have to keep track of that, right? That seems like it would be important. The reason you don't have to keep track of that is that adding and removing electrons, because we were saying we were in an insulating state, that means that it costs a finite energy to add or remove these electrons. All right. And it turns out that for this topological state, unlike the integer state, it is not really those electrons that provide us this fractional Hall resistance. It's really, in a sense, the anyons. And so if you know what all of the anyons in your system are, you know their charges and statistics, you can ask the question of what happens if I apply an electric field, and just ask what does that long-range entangled order of the anyons do in response, and that will spit out the answer for you. All right. There are many, many different ways of seeing this mathematically. One way to see it is something called the bulk boundary correspondence. The bulk boundary correspondence is just the following. In the bulk, I have this topological theory where I have to keep track of these funny anionic particles that have strange charges and strange statistics. And those bulk topological defects, if I have a system with a boundary, turn into the boundary currents that flow. All right, so you may remember, last week we talked about this following fact. If I have an integer edge state, for every integer plateau that's filled, I know that I have an edge current, and that edge current carries 1 unit of charge for each 1 unit of charge in the formula for the resistance. If you ask about how that charge flows and you look at Ohm's law, you immediately find that if I have n integer fillings, then the Hall resistance is h over n e squared, which is the usual integer formula. You can redo that analysis using this so-called bulk boundary correspondence, and the only thing that changes in that analysis is that my edge mode doesn't carry charge E, it carries charge E over 3, and this is just an immediate consequence of having these topological defects in the bulk that carry charge E over 3. Right? It's not that I have one of these topological defect anyons running along the boundary. It's that if I ask about the topological structure in the bulk, that's equivalent to talking about these edge currents on the boundary. And so you go through the formulas, and you say, the only thing I have to change is that my edge current carries along with it charge E over 3 instead of E. I go through the formulas, I say these currents have to flow, so some voltages match, some voltages don't. I use Ohm's law, and Ohm's law tells me that the Hall resistance is h over 1/3 squared, which is, again, h over nu E squared, where nu equals 1/3, which is exactly what these people saw experimentally.
What are the red X's for? Wouldn't that whole thing be a loop?
No, sorry. So the point is that I'm driving a current this way. Sorry. So this is something that I discussed a little bit last week. Maybe I should refresh our memories. So I have these edge currents, but there's something very important about these edge currents. They can only flow in one direction. Okay? So they can only flow, let's say, to the right on the bottom and then to the left on the top. Now, the experimental setup I'm doing here, let's talk about this for the previous state. So the experimental setup I'm doing here is that I'm driving a current from here to here, and then I'm going to measure voltages across these guys. And so the point is that I'm trying to drive a current this way, but at this point of the sample, the currents can't flow this way because it can only flow to the left. And similarly, I'm trying to pull it out here, but it can't flow. So what ends up happening is that as I go through this calculation, I say, if these are the only ways that currents can flow, and there's obstructions here, because these currents can only flow in certain ways, then 1, 3, and 4, but not 2, have to have the same voltage. Have to have the same voltage, and 2, 5, and 6 have to have the same voltage, and then you just go through using Ohm's law. Sorry, V is the same as delta mu. It's just a nomenclature difference. So it's because these currents are special, they can only go in one direction. And so similarly, here the currents can only go in one direction, and so the voltage here can't be the same as the voltage here can't be the same as the voltage here, and if there's a voltage differential here, even when I'm driving a current, that by Ohm's law tells me that there's a resistance. It's a little non-trivial that if I look at this formula, it also looks like the normal resistance is 0, but this is something that I've mentioned previously. When I have this odd resistance, non-zero, the resistivity is a matrix, it's not just a set of numbers. And to go from conductance to resistance, you have to invert the matrix. And so it turns out that if the Hall resistance is 0 and the normal resistance, sorry, the Hall resistance is non-zero and the normal resistance is 0, it's an off-diagonal matrix. When you invert it, you just immediately find that the normal conductance is also 0. So even though it seems like a misnomer, it seems like I'm saying it's a perfect resistor in this direction. It's actually an insulator at the level of I can't move charge in that way. So I should just mention that if I have other fractional plateaus, right, there's that whole host of other ones, there are different non-trivial topological theories that describe them, right? There's going to be a different set of what the topological defects are, what their charges and statistics are, that you can basically fix, and you'll kind of, again, you'll get this fractal edge current and you'll measure it. And then, so, right, seeing these fractional edge currents is just something that you measure directly when you look at the Hall resistance. Now, I told you that these things have fractional statistics, and we believe theoretically that that's the case, but that's an extremely difficult thing to measure, right? Anytime you're measuring, to measure that, you have to do some very delicate interferometry, and it's a hotly debated question whether or not the experiments that people have done trying to observe those fractional statistics actually have observed them, or if it's other sources of issue, right? It's just a much harder problem to do. People here at the University of Chicago, like Rowan Kang, have worked on this for a long time, and it's just a very, very difficult experimental problem. Something else that I want to emphasize is that for this 1/3 state, kind of because we had this beautiful guess for the wave function, we kind of knew uniquely what the topological theory was, right? Because we knew what the wave function was. There are plenty of states where those nice arguments don't work. So for the 1/5 state, you can just follow through this. For the 1/5 state, you won't be surprised to learn that you get something that has charge 1/5 of that an electron, and its statistics are -1 to the 2/5 instead of 2/3. But that's because, again, you can write down the wave function. There are lots of plateaus where we don't know exactly what the wave function is. And so you can write down different topological theories that would give you the same, say, Hall resistances, but might look different in other ways. A great example of this is there's something that I didn't talk about at all. There's a plateau at filling fraction 5/2, and a current, and so that's a very special state, mostly because of the even denominator for reasons that I'm not going to talk about too much. You can ask me afterwards. But there's an open question in that. It's something that's observed experimentally, and people are very curious. Does that state have regular anyons in the sense that if I take one anyon around another, I just get a phase? Or is it non-abelian in the sense that if I take one anyon around another, I don't get that same state up to a phase. I can take one state around another and get a linear superposition of different defects. And so if that were the case, that would be very useful for quantum computing, but it's just not actually known. You can also write down much simpler theories that also describe that 5/2 plateau. So, if you know the wave function, you can deduce the topological theory, but it doesn't quite work the other way. Yeah. So with that, I'll wrap up. So next week, I'm going to talk about, since we know that there are these funny defects that can have these very funny braiding properties, we're going to talk about how those funny statistics and braiding properties could potentially be used to build quantum computers. Thank you. You can only kind of follow the edge in one direction. You can think of this as being related to the fact that in the bulk, my electrons are moving counterclockwise and not clockwise. So if they're moving counterclockwise, then on the edge, that direction is in this direction. On the bottom, it's the other way. Yeah, sorry. Yeah.
Okay, and those red X's, energy cannot flow through that one line.
Voltage can't be driven this way because it's the wrong direction for the way in which charge can flow here, or the way in which this edge mode can flow.
So evidently, is it going to edge and flip the flow through that voltage into the current?
Sorry, say that again.
So like if you flip it, like that, can you get a current flow through there?
So this is the standard experimental setup. I don't have to do it this way. I could, for instance, apply a voltage differential here and ask about current flows in various regions.
Oh.
I mean, so you're always looking at Ohm's law, and so the question is, are you applying the current or are you applying the voltage? Or you can always do one and measure the other.
Could you go back to the equations of the defect?
Sure.
Let's say that.
You mean the wave function?
Oh, wait, okay.
Yeah.
All right. Does that ever go to zero?
But zeta?
Yeah.
Zeta is just the location of the defect. So I can put in at the level of, this is just something that tells me about the electrons, right? So I'm just asking what the electrons are doing. I see that they see a defect that they can't get too close to. Because if the wave function, so this is the location of the defect, and this is all, and so I have kind of every electron's coordinate minus the defect's coordinate. So anytime an electron tries to get close to the defect, the wave function goes to 0, which tells me that the probability of finding the electron there goes to 0. And so so the generalization to talking about allowing the defects to move around and studying their statistics is a bit of a generalization from just looking at this that I didn't talk about. It is more, you can't, I mean, you can start with this and then do some generalizations to figure out why this guy has charge 1/3, why it has these funny statistics and so forth.
Okay, so then would you say that it decays then into the multiple locations that move around?
So once I allow this guy to move, it's free to move wherever it wants. That's different from saying that, so I could consider a state where I have more than one of these guys. They energetically, if I have 3 of them, they actually don't energetically prefer to form up into one electron. That makes sense, right? Because they all have positive charge, so they're electrostatically repelled. So that's precisely the reason that, where's my picture of it falling apart? That's precisely the reason that since I can break this up into smaller pieces, they'd much prefer to do this because they're all repelled from each other.
So these are then virtual positions, or are they calculable?
So, well, okay, so
The function, are they calculable?
the wave function that I wrote down was a wave function that told me the following. If a defect is in this location,
Yes.
what are the electrons doing? There is then a generalization of that to asking what is the defect and all of the wave functions. What are they doing all together, in combination? But I can't do that at the level of the wave function. It's a slightly more complicated.
So essentially, you're measuring the effects or projecting the effects.
You can measure the effect of the existence of these guys because you can do some.
Right, but the location of the defect is only
It's only known from It's only known
from its
probabilistically.
effects.
Yes, but I mean you can think of these defects as they are still quantum objects. So in the same way that I like to draw pictures of pulling an electron out and having a defective charge. When I'm really just talking about the electrons, I can only talk about the electrons in terms of say what their probability distribution is. Right. And so similarly, when I build up the full theory, I have to talk about the probability distributions of the electrons and these quasipoles or anyons. It turns out that since it's lighter to move these guys around than the electrons, then what you can do is basically say, I'm going to ignore the electrons and assume that the excitations that I'm looking at are just these topological defects. That's how I get to the topological theories, that I say, I'm just going to kind of ignore what the electrons are doing because for some things I'm allowed to do that. So for instance, when I try to measure the Hall conductance, I don't actually need to know what every electron is doing. There's a sense in which you can kind of integrate them out. Yeah.
So looking at this picture of charge density at different nu, 1 and 1/3, that to me looks a lot like probability of, as it relates to position.
So I
in
mean,
space.
I want to make sure I'm looking at the right picture.
Position in space.
This picture?
No, this one with the dots.
Oh, sorry. Yeah. Good. Oh, yes. So yes. What was your question?
So that to me conceptually looks like a representation of the function of
Sure. So yes.
giving a probability of a distribution in space.
Yeah, so what this picture is, I mean, this is always a cheat, right? It's very hard to, there's no way to draw a picture of the probability distribution for a bunch of particles, right? Because that's something that lives in a space that's 2 to the number of particles you're looking at, and you just can't draw that. So what I'm drawing here is I'm basically saying that if I want to ask, say, using the probability distribution of this wave function, what's a likely location that you could find all of them in?
That's not my question. It's sort of preliminary. So you've been talking about a lot of things today that, frankly, much of it went over my head, but you're talking about charge itself, and fractional charge. You mentioned energy. You're always talking about strength of magnetic fields here. And one of the things that I remember you saying in one of the early, more fundamental lectures was that the wave function, you want to emphasize it contains more than simply probability distribution for position in space.
Yes.
So what I don't understand, I wonder if you can tell me, is can you list a few of or all of the properties or states or things that the wave function addresses? And the real question I'd ultimately like to know is, are all of them always expressed as a probability, which is a square of some absolute value of an amplitude relative to that property? Is the question clear? What are the things that the wave function expresses?
So let me make an analogy. So if I was just talking about classical probability theory, right? In classical probability theory, if I'm just talking about the classical probability to find a particle, then the way you actually do that is you say, classically, a particle can be at a point and it can be moving somewhere, right? So a classical probability distribution is different from a wave function in the following way. It is a function of both a position and a velocity, okay? And those two things can be independent. Now, there's a wave functions are different in the following way. Wave functions, as we normally write them, are just a function of a position. But they have more information, right? So that sounds like it's just a local probability distribution. But it is more than that, because you can extract from the wave function, for instance, the probability of finding the electron at some velocity, you know, or at some angular momentum.
A probability, it's a velocity probability. So the thing that you're addressing in this function that's not position is velocity. And from what you just said, it seems like the answer to my question is that insofar as it addresses velocity, it's always a probability of a velocity.
Yes.
Yes.
And so the standard interpretation of quantum mechanics is a probabilistic one, right?
So that would include charge.
No. So that's a good question, right? So you can ask kind of what probabilities are there. So if I'm talking about an electron, you can ask in the framework of quantum mechanics, what's the charge of the electron? I don't care where it is, just what's the charge of it? And there you don't get a non-trivial probability distribution. You get no. The charge is always -1, or -e, right? So you could, if you wanted to, interpret that as a probability distribution, but it's one where it is always -1. Unlike position, where it's really always technically, there is some spread. Even if I try to make an electron very localized at a position, we know quantum mechanically it always has some finite spread. But if you ask what the charge of the electron is, it's always -1. It's not a distribution. It's really just a fixed number.
And is charge in that function?
In this function, well, so you have to ask in the framework of quantum mechanics, there is a way of asking what is the charge of an electron. And when you grind through the machinery, you don't get a distribution of, oh, it could be charged 0.9 or 1 or 1.1. You just get 1 or -1.
Okay, one last question. Is there anything else besides charge that's in that function that that you haven't mentioned yet. So I'm just trying to find out what are these functions about.
So the way it works is the following. So like I said, it's similar to classical probability theory, where you have some probability distribution of where a particle is and what its velocity is. Okay, but the point is that here you can't ask those two things independently. So in particular, let's say I ask a probability distribution for where a particle is, and then I measure it to some kind of finite, right? I can only measure things so sharply. If I try to measure it to some sharpness, that tells me, unlike in classical probability theory, if I do the measurement and I pick something that's, say, highly probable, because that's what's likely to happen, then you will find that the probability distribution for its velocity has changed, because you changed the state by measuring it. That's the sense in which it's different. So basically, anything that you want to try to ask about observing in the system, there is a way of formally asking that question in quantum mechanics. And for many things like, what's the angular momentum of the electron? What's the spin of the electron? What's the position of the electron? Quantum mechanics will tell you a probability distribution. But there are some things that are fixed, like the charge of the electron. Right? That's something that you don't have a probability distribution for. So you shouldn't think of these topological defects being charged 1/3 as, it's close to 1/3. Like the electron being exactly charged minus E, each defect has exactly charged plus E over 3.
Is just fine point on that. This is a different concept than its probability of 100%, or no?
I would say yes. Asking about the charge of a particle is different. It's different than asking about its position or its velocity, because charge is related to conserved quantities. So the total charge is fixed, and so there are kind of two pieces to that, right? The total charge is fixed, and things are made up of fundamental discrete quanta called quarks and leptons, and assuming that you don't have, if you ignore substructure below that, then those are the discrete pieces of charge you can have. And so even if I say, I build some proton out of some quarks, and so there's a non-trivial question of, I take the proton, I can say the proton has a charge, and it has some non-trivial probability distribution for its position, its momentum, built out of its wave function, and then I zoom in and I see the quarks, and I can say, well, what's the probability distribution for each quark relative to the other one? But again, once you zoom in on each quark, you see each quark individually has a fixed charge. So I would say things like charge are really different than asking questions about, say, position. And that still holds true even in a even more strange theory like in string theory. If you talk about what, when you zoom in closer, gave you things that macroscopically look like electromagnetic charge, they are still things that are not fuzzy quantum mechanical features of a particle, but are just hard and fast fixed numbers. Yeah.
I'm afraid. Is the spin of electron, the rate at which an electron spins, the revolutions per second, is that a constant in nature, or does that vary?
The rate at which it spins is fixed, and it's just h bar over 2. So that's not quite the rate. H bar, this tiny, tiny, tiny number, is in units of angular momentum. And so if you assume that you kind of make your electron fuzzy and it has some de Broglie wavelength, then you can ask, okay, if I have a ball that big and it has this angular momentum, how fast does it spin? So I would say that the speed of the rotation isn't really something that's fixed. It's the total angular momentum, right? But that's, if I have a very small ball and it's spinning, they'll have different angular momentum if it's very big. So you have to be careful. But the magnitude of the angular momentum of an electron is something that is just fixed. Now, angular momentum is rotational on an axis, so the direction of the axis can change.
Yeah.
But the magnitude of the angular momentum is just a fixed constant, like its charge is a fixed constant.
Okay.
Yeah.
I was going to say for the gentleman in the middle, there are couple books. There's one, Schwam, S-H-U-A-M, and there's even a dummy book for quantum physics, and they basically describe the wave function from a historical standpoint, and also the attributes for that function. So it's an easy layman's read. I mean, I would try, well, no more borders, but try a bookstore, go through the science section. There's a lot of books that are at the layman level. I mean, so that's where I would go. and then I show my ignorance. Can you show that one picture where you have the orbitals?
The cyclotron going in orbits?
Within the electron orbits?
So, you mean in a previous talk, or?
I know the slide here. Yes.
So these?
Oh, I thought, okay, well,
These?
I thought those were the electron.
Oh, sorry, yeah, so let me guess. So these are not the orbits of the electrons. This is basically, the wave function is a function. And so this is right here is kind of a height map of it. And so the idea is that as I allow the wave function to evolve in time, there's a sense in which this electron is rotating, right? In the sense that if I look at the wave function in time, the whole wave function is just rotating. Like you know, in the way that I can imagine, say, a standing wave in a bucket can be rotating. It's of course not exactly that, but it's kind of similar. You should think of it that way. These are basically standing waves, right? This is again, you know, I have a standing wave, and that standing wave has some fixed angular momentum.
Okay, this is where I'm showing my ignorance. I've seen pictures where I was under the impression that the model had the electron, the photon or electron, and it clouds in a cloud.
Yes, yes.
Orbital 1, orbital 2, orbital cloud. I've seen other models where they'll show the cloud like they're teardrops.
Yes. So that's something different. So that's yes. You really asked the question of what is the wave function for an electron surrounding, say, a hydrogen nucleus look like, and so what those pictures are, those are exactly pictures of not the wave function, but the probability distribution for the electron. And we find that it does kind of look like a cloud, and in the S shell, it's just a nice spherical cloud. That there are different higher energy orbitals that you can have. And in those higher energy orbitals, yes, it can kind of look like there are these pear shapes because it's some higher angular momentum. Okay. But yeah, so that's a little different from here. You can think of there is a rough analogy, but there it's really an electron orbiting a hydrogen atom. Here I'm talking about a different question of what does the electron look like while the electron is trapped in a plane and kind of feeling a magnetic field. Yeah?
And then the picture where you were showing the current flow not going in one direction,
Yeah.
but going in the other direction with the two axes.
Yeah. Yeah.
Is that, that's in one piece of material?
Yeah, so this is I talked about this a little bit last week. So the idea is that for the integer case, there's you'd like to talk about all the electrons being spread out in the sample, but what actually physically happens is that because of the fact that the system isn't perfectly clean, and you can kind of think of that as these electrons, in a classical point of view, are kind of rolling in a very gentle but sloping terrain. And so what happens is that electrons that are in the interior will generically get trapped, kind of stuck in little valleys of the terrain. And so they don't drift. And the only thing that actually can give you a flow is electrons near the edge. Because if they're near the edge, they kind of want to get trapped in some valley, but then they bounce off the edge. And so the electron is basically kind of bouncing along the edge. Right? Because it wants to orbit, but every time it hits this, it has to bounce off because there's a physical edge there. So that's the reason that this has this orientation. Right? And this guy really wants to rotate and bounces, rotate, bounce, etc.
But that's the one, that's not separate pieces of material.
No, yeah, this is all one slab. I'm just asking where is there actually charge flowing. And then if you look inside here, you'll find that there's basically nothing flowing. Now that seems funny because it looks like, well, there's a current going this way and there's a current going this way. So why is there not a conductance, right? And the reason is that, well, no, it's the same here and here, and so you can roughly think of it as, if I think about the net current in this direction, these two things cancel. Unless I apply a voltage differential. If I apply a voltage differential, then there will want to be more electrons bouncing on one side than the other, and if there are more electrons bouncing on one side than the other, then they don't actually cancel in the net current. And so that's an analogy about electrons going in cyclotron orbits, and I just want to emphasize that you can't directly make that leap to this picture being about these charged 1/3 anyons moving in cyclotron orbits. It's not exactly that. You do at the end of the day have this edge flow that carries this much current, but the analogy to cyclotron orbits is broken down.
I was curious, say a candy bar shaped slice of superconductor. How does the current flow in the superconductor? Is that in the center, evenly through, along the edges?
So a superconductor is special. It is a perfect conductor, hence the name, in the sense that if I apply a DC voltage, it conducts perfectly, right? So if you look at this formula, so what a perfect conductor means the conductance is 0. The conductance being 0 means that the resistance is infinite. So that means that any time I apply a voltage, the current immediately, with no backscattering, aligns itself to exactly cancel the voltage. So you try to apply voltage, and it automatically goes to 0 because the resistance is infinite. Or sorry, no, I got that completely backwards. No, the resistance is 0, and so I apply any voltage, and I get no current flow. Sorry, yeah, the point is if I try to drive a current, the charge carriers will cancel it. Yeah.
So the electron will flow evenly distributed through the whole.
If I'm applying a DC voltage, now there are other things that I can do. I can try to drive a AC current through the sample, and if I try to drive an oscillatory current through the sample, then it won't conduct unless I make the frequency of that current large enough.
The question, I think it was, if you have a cross-section of the conductor, the density of those electrons is equal on the whole area.
Yes, at least on kind of a non-super microscopic scale. They're all just moving together, like a nice fluid.
Okay. Yeah. May I ask lastly, on your nice graph, back to this graph again.
Oh, sure, yeah.
Resistance and the magnetic field.
Yeah.
May I ask, yes. So, may I ask, so on your x-axis is your magnetic field.
Yeah.
Your y-axis is resistance. Is that correct?
So you should be careful. So this is that odd resistance where I apply voltage in one direction and I measure a current in the other direction.
Okay.
This other axis, you should really think of it as the normal conductance, in that I apply a voltage in one direction and I ask the current flow in that direction. And so what's happening in here is that I apply a voltage and there's current flow orthogonal to it, but there's no current flow in the direction of the applied voltage differential.
Here's my question. What is the effect of temperature in that experiment? Is it negligible when you go through the various plateaus?
So this is in an ultra-cold limit. So that's a very good question, because I can then just pull this other plot up. So here you can see the effect of temperature, right? Because they go from about 4 Kelvin to half a Kelvin. And so let's look down here again. It's called rho. You should think of this as the conductance. And so in each one of these curves, you see that in this curve, this is a little misleading because these are offset. But you find that at moderate temperatures, it does still conduct as you'd expect. But as you cool it down, you get this broad plateau where it does not conduct normally. Now, in these samples, this isn't quite cold enough to see this as really being solidly insulating. This system is at a colder sample, and that's why this looks like a much sharper zero than if you try to extrapolate this zero line out to here or this curve. It's clear that it's approaching zero, but they're actually a little bit nervous because it's not immediately obvious that this is really approaching zero or some finite value, but it turns out that it is. So basically what happens is that as you cool the system down, two things happen. You get these plateaus, and they emerge, and they get broader the colder it gets. And underneath those plateaus, you get the normal conductance going to 0.
Is that zero, absolute zero, very, very cold?
I mean that what you find experimentally is that if I kind of try to fit what the actual finite number is as a function of temperature, I believe in these cases it's going to 0 exponentially in temperature.
Okay.
So, you know, the colder I make it, in the idea that it's, you know, e to the minus some energy scale divided by the temperature, right? Divided by the temperature means that the lower the temperature gets, the larger that prefactor in the exponential is, and it's e to the minus a huge number, so it gets very 0 very fast. Which is actually very similar to what happens in superconductors. Similarly in superconductors, of course, a DC voltage gives me perfect conductance, but if I ask about these AC conductance at some finite frequency, you'll find that at finite temperature, it is non-zero, but it also approaches 0 exponentially. That approaching 0 exponentially in temperature is intrinsically related to there being a finite energy gap to excite electrons, right? If I'm at finite temperature, I can use those thermal fluctuations to excite those electrons, but the colder it gets, the weaker the thermal fluctuations are, and so the worse of a conductor it is, when it's, if you could really even call it a conductor. So that in the limit of being at strictly 0 temperature, it's a perfect insulator. But of course, in the lab, you never get something to really 0 temperature. You can just do as the best you can. I mean, it's, there's this experiment was done in 1982, or the paper was published in 82, and this was published in 92. So it's, not unreasonable to think that there was some great experimental improvement, and that's why this looks so much better like a 0, as opposed to this, which doesn't really look as 0. Yeah.
Interested when you talked about the single layer, how you could project this to regular matter.
Sorry, the single.
Well, this is all.
This is all on a plane.
Two-dimensional.
It's all effectively. I mean, it's obviously not exactly two-dimensional. It's something done in a laboratory. I don't have the picture on these slides, but the idea is that I have some substrate grown on. I have some substrate, and I have some material very thinly placed on top of it. And so if I kind of zoom in and just say, if I ask what the actual electrons are doing there, it's much, much easier for them to move in plane than for them to try to move out of plane. You can roughly think of that as if they're basically, yeah.
Yes. What my question really is, from this, project this to normal physical possibilities. In other words, you're not likely to get that situation. Is that possible to consider materials that you could actually stack to be able to do this?
So you can certainly try layering things, but you have to be careful, because this whole story of it being a good insulator doesn't work as soon as electrons are actually free to move up and down in the z direction. There are other interesting topological materials that exist in bulk 3 dimensions instead of 2 dimensions. They look different than this, though, and there aren't as many of them, and it's hard. Here, there are some special mathematical niceties of this being in 2+1 dimensions, like the fact that I can have arbitrary grading statistics. Is one of the reasons that I can have a kind of broader spectrum of interesting stuff happening in 2+1 dimensions than 3+1 dimensions. But there certainly are. You don't get things that really look like this, but you do get systems that have non-trivial topological defects like the anyons in 3 dimensions. That is definitely something that does happen that I will probably talk about not next week, but hopefully at least a little bit in the last week. Yeah.
There is still the problem of having a monomolecular layer on some substrate.
Yes.
And the substrate is going to attract something.
Yes. So that's the hard part. So
is that where the defects are theoretically?
Yes. Well, the defects come in 2 places. That the substrate, which if you don't know the terminology, the idea is basically the following, right? So the substrate is some chunk of material that you then layer a thin layer of something else on top of it. So it's the substrate, right? So if that substrate had a perfectly flat top, and then I put the layer on top of it perfectly cleanly, then of course there would be no disorder and things like that. But it never actually works perfectly like that. There's always there's a balancing game, right? Because as I argued previously, if I have a absolutely perfectly clean sample, then you would never see plateaus, right? Because these plateaus only exist if I can wiggle a little bit away from having exactly the right magnetic field. However, if the system is really dirty, then what ends up happening is that, if I go back to this picture, if the system is too dirty, everything is localized. I never get these extended states. And if I never get these extended states, it's never going to look like a Hall conductor. It's just going to be a trivial insulator the whole way. Because the idea is that if it's too dirty, it's not that I have cyclotron orbits that get trapped in soft valleys. I get that every electron basically gets stuck to dirt. Okay. And then, yeah.
In the two-dimensional model, when you remove an electron, you create the 3 defects.
Yeah.
Can you remove a partial charge?
No. So yes. So this is related to a question that was asked earlier. Let's see if I can do this faster. So it certainly is the case that. Lost it. Here we go. Great. So the question is, right here, I pulled out 1 electron, I left a hole of plus E, and it's split into 3 things that were E over 3 because they're electrostatically repelled. Right? So the question is, can I just remove one of these guys? Right? And that would be wonderful if you could, but you can't, because this is a crude picture, like everything is, right? It's not really something that's localized. Just like the electron, it has some non-trivial probability distribution. So what you might try to do is and moreover, in a quantum mechanical wave function sort of way, these 3 guys, by nature of them being created this way, are very highly entangled with each other. And if I had other guys over here, they would also be entangled with them. They have to kind of quantum mechanically know about each other in some very subtle way, so that as I exchange any 2 of them, I get this very funny phase. So what that means is that these guys aren't really as localized as they seem. So if I wanted to try to remove one of these guys, what could I do? I could imagine cutting the sample, where if I believe that this guy is very likely to be over here, and these guys are very likely to be over here, in some probabilistic sense, and then I cut the sample and ask what I get, you might think that, oh, I have a fractional charge here and a fractional charge here, but that can't be what happened, because to cut the sample, I end up breaking the non-trivial entanglement between these guys, which destroys their special topological status as things with charge E over 3. So if I actually tried to cut the sample and break it, this notion of having these defects breaks down at any guy across the sample, and so you would always get an appropriate integer number of charges. So there's no way to just take one of these guys and remove it.
Okay, if you can remove an electron and create the 3 defects,
Yeah.
can you remove a hole and create the same effect?
Good question. So removing a hole would be the same thing as putting in an additional electron. And I didn't talk about it here because for technical reasons, you can do that, but they're much uglier objects. They're not for reasons that come from the fact that I have this background of many electrons. So there's an asymmetry between positive and negative charge. And so basically because of that asymmetry, a plus E over 3 particle can look very different than a minus E over 3 particle. And in particular what it means is that even though these guys are kind of non-trivially entangled, there's still a sense in which they can be thought of as localized defects at the level of asking what charge density locally is. But if I try to add an extra electron, it will fragment into things that are much uglier and aren't localized in that nice way. Yeah. You can think of those the minus E over 3s being very ugly is the reason that I only have to keep track of these guys to calculate things like the Hall conductance. So if I think of these as quasi-poles, because they have positive charge, a quasi-particle is something that can exist, but it's this broad, messy lump of gunk that doesn't contribute to edge physics the way that these guys contribute to edge physics, because of the fact that there's an obvious charge asymmetry.
What happens if you were to take your sample and make a diagonal cut, then you have your defects, and what happens if you were to place those two cuts back together? Would you go back to your prior state?
So, okay, that's a good question. So what would happen is that if I ended up, so let's say I cut the sample through here, but I do it perfectly clean so I don't change the number of electrons. But I break the wave function in half. And so what will happen is that with some probability, I will find the hole on one side. With some probability, I'll find the hole on the other side. Okay, but then let's just think about the side that has the hole. If I didn't do too bad, okay, I'll break it. Breaking that is a projection, because I'm doing something hard to the system. And so then I look at the side where I know the hole has to be, but then that in and of itself is a nice isolated quantum Hall state, and it will fractionalize. As soon as I stop drastically doing things to the state. So what will happen is that I will cut it, and then I will have these three guys over here. And then I can try to glue that other thing on. And gluing it on is not as disastrous as cutting it. So I'll glue it on, and once I glue it on, then, so I cut it, let's say I find the hole on one side, but then I let that thing sit still so that one hole fractionalizes into three quasi-holes. And then I slowly glue that remaining piece back on, and that just means that those guys, if they want to, can wander into that other region.
So what would happen to take your sample and instead of cracking or cutting it, bend it? How would that affect?
That's a very good question. So bending the system is actually a very interesting topic, because I'm talking about this as if it's a topological theory, and usually topology means you only care about kind of overall shapes, like is it a donut or a ball. But it turns out that these systems do actually have non-trivial, not yet experimentally verified response to curvature. And in particular, so we talked about this number nu, which is 1/3, which is this topological quantum number telling me, say, how much charge is there in relationship to the applied magnetic field. So that's one question. And you could also ask, and so the idea is there that if I change the magnetic field locally somewhere, like I make the magnetic field a little bit stronger over here than over here, then what will happen is that you'll find more charge in that region. This is something that I'm not sure has been very cleanly experimentally verified, but it's believed to be true, and probably at least to some degree it's been seen. So you could then ask the following question: what happens if I curve the system a little bit, right? And the answer is that, I didn't talk about it here at all, because I didn't think anyone would ask the question, but I'm glad you did, since this is actually a subject of my current research, is that if you take, you can't actually physically do this, it's very difficult, right? Because if I curve the sample, the magnetic field is no longer strictly exactly out of plane, but you can do the thought experiment of saying, say I bend the sample and change the magnetic field so it's still exactly perpendicular, and then you can ask, do I get more or less or no charge in that region of curvature? And the answer is that for these particular states, you get a little bit more charge. But it's a number that's different than nu. It's a different number called the shift. And you can think of the shift coming about in the following way. Okay, I have the sample, and it's in finite volume. So there's a set number of charge to fill up each Landau level. So let me just talk about Landau levels, though this notion of the shift generalizes. So in this picture, I always told you guys that the number of states here is the magnetic fields times the area. Okay, so it's a ball. So I can imagine doing the thought experiment of wrapping that bar up into a cylinder and then closing it into a torus, still perfectly keeping the magnetic field lines pointing always directly out of it. Okay? Then that system there is some curvature, but the topology is that of a torus. And a torus has net curvature 0. You can think of a torus as having net curvature 0 because on the outsides it's positively curved, but on the edges it's negatively curved. And if I integrate the total curvature of a torus, it's always exactly 0.
Is a torus
a torus is a donut.
A donut,
Yeah.
yes. Okay.
So there's at the top of the torus, there's positive curvature, but kind of underneath the handle, there's negative curvature, and they just cancel. So then imagine the following question. Imagine that I don't take this and I wrap it up into a torus, but I wrap it up into a sphere, and I still perfectly have the same amount of magnetic flux piercing the sphere, right? And I keep the area the same. And then I say, how many states are there in each Landau level, right, for the system on a sphere? And it is no longer the magnetic field times the area. It is the magnetic field times the area plus an additional number. And for the lowest Landau level, that number is 1. For the next Landau level, that number is 3. So it's a tiny macroscopic change if the magnetic field is big. But as a thought experiment, it's a real number that is quantized. And it has to be quantized because I'm counting the number of states, right? So that thing that is the shift there counts the number of states. And that same number tells me if I curve my sample a little bit, locally, how much more charge do I get? So response to geometry is actually a hotbed of current research right now. So it is a question we're thinking about. The much harder question is how do you try to measure these things experimentally, right? I say that there's this additional number coming from bending the surface. What experiment can I do to try to measure the effects of this thing's response to curvature? Is there anything you can do? Yeah.
I was going to say, what was that research that you said that the University of Chicago was currently experimenting with this looking at quantum answer? Is this something that...
So I don't know the most up-to-date statement, but my understanding as of a little while ago is that, so there's this question of, you have these topological defects, and we believe they have fractional charge and fractional statistics. And there is experimental evidence that you do have in the bulk things that can carry fractional charge. The much harder question is, can you determine that they also have fractional statistics with each other by doing some kind of nuanced interference experiment? And people have been working on that basically since it was conjectured that these things existed. And I don't think it's conclusively stated, even for this 1/3 state, whether or not there really are fractional statistics. I'm not 100% on that. I know that for more complicated states, it's a solid question, what statistics do they actually have? Yeah. Any other questions? Thank you.